Hi there, and welcome to the final lesson in our series, Introduction to Electronics. In our previous lessons, we investigated what happened when we applied potential difference to the ends of different types of materials. We found that metals obey Ohm's law and are therefore classified as conductors. Plastic materials do not generally allow charge to move through them and do not obey Ohm's law. They are called insulators. When the potential difference applied across the end of an insulator and the temperature are very high, the insulator may allow charge to move through it. This is called electrical breakdown. And in our previous lesson, we began to explore the world of semiconductors, such as silicon. We found that at low temperatures, silicon behaves as an insulator, but at high temperatures, it behaves as a conductor. Scientists have found that they can make silicon behave more like a conductor at lower temperatures by adding an impurity to the silicon crystal in a process called doping. The impurity may be an element with one more valence electron than silicon. In this case, an extra electron is added to the silicon lattice, and an N-type semiconductor is formed. But if the impurity is an element with one less valence electron than silicon, there is a shortage of electrons and holes form in the silicon lattice. We say that a P-type semiconductor has formed. To explain our macroscopic observations, we used a model of what is happening at the microscopic level called energy band theory. In all materials, the energy levels of individual atoms overlap to form energy bands. The energy band that contains the outer electrons is called the valence band. The energy band that is formed by empty energy levels after the valence band is called the conduction band. In metals, the valence band and the conduction band overlap. So when a potential difference is applied across the ends of a metal, electrons gain energy and can move freely through the conduction band. In plastic materials, there's an energy gap between the valence band and the conduction band. When a potential difference is applied across the ends of a conductor, the electrons do not have enough energy to move from the valence band into the conduction band. So these materials are insulators, unless the energy is great enough to overcome the energy gap. In silicon, the energy gap is not as big as in insulators, and so when a little heat is applied to silicon, electrons can be pushed into the conduction band, leaving empty regions called holes in the valence band. It is this difference in the way silicon behaves at high and low temperatures that enables it to act both as a conductor and as an insulator. In other words, as a semiconductor. For N and P doped semiconductors, the energy gap is reduced even more. In N-type semiconductors, the extra electrons occupy an energy level just below the conduction band. And for P-type semiconductors, the holes occupy an energy level just above the valence band. As a result, doped semiconductors behave like conductors, even at lower temperatures. So far, we have seen how conductors can be used in electronic circuits as resistors to control the current. We have also seen how capacitors, containing insulators, can store charge and so also regulate the potential difference in a circuit. You may also have heard that semiconductors are used in silicon chips and that this invention led to the start of the electronic age. But how do different semiconductors actually work? Well, in this lesson, we will start to answer this question by having a closer look at what happens in two components found in many electronic circuits, the diode and the light-emitting diode, called an LED for short. both the diode and the LED are used to control the direction of current passing through the circuit. Both of these components are made from a combination of P and N-type materials and get their distinctive properties because of what happens when P and N-type materials are joined in what is called a P-N junction. By the end of today's lesson, you should be able to describe what happens when a diode or an LED are connected into a circuit, and use energy band theory to explain how a diode controls the direction of current in a circuit. Well, I really think we need to start by doing some practical investigations to see how a diode works in a circuit. Let's join Tate and the learners in the lab. I'm sure they won't want to miss a chance to do more investigations.
Hi there. My assistants and I are set up and ready to start the investigation. Have a look at the circuit we've set up.
The circuit we will use during this experiment is similar to the one we used for testing conductors. Here we have a power supply connected to a rheostat, an ammeter, a switch, and a diode connected in series. We also have a voltmeter connected in parallel.
Can we get started right away?
Sure. Just follow the instruction sheet and remember not to increase the current to more than 50 milliamperes. Diodes are designed to work for small current values and will be damaged by high current. Right, the learners have collected the readings of the current passing through the circuit and the potential difference across the diode. So, what have we found?
Well, this diode definitely doesn't obey Ohm's law. Look, even when the current was 0, we noticed that the voltmeter reading was 0.1 volts. And when we increased the current, the voltmeter reading increased for a while, but then reached a constant value.
So when we graph these readings, we get a curve that does not pass through the origin.
Okay, let's analyze the graph together. Here we see that there's a potential difference across the diode before the current passes through it. But then as the current increases, the potential difference does not increase proportionally. The gradient of the curve changes, which means that the resistance of the diode changes too. Notice that the potential difference reaches a maximum when the current increases to more than 30 milliamperes. To explain our results, I think we'll go back to studio. We will take a closer look at what happens inside a diode, where the N and P-type semiconductors join together.
Thanks, Tate. Now, let's take a look at the energy band theory model of what happens at a P-N junction to see if we can explain the results that the guys in the lab found. Remember, a P-type semiconductor has holes just above the valence band, and an N-type semiconductor has extra electrons in an energy band just below the conduction band. Now, when a P-type semiconductor is joined to an N-type semiconductor to form a P-N junction, something very interesting takes place. Free electrons in the N-type semiconductor drift across the junction and fill the holes in the P-type semiconductor. This means that the atoms that donated the electrons now become positively charged ions on the N side of the junction, and the atoms that accepted the electrons becomes negatively charged ions on the P side of the junction. The positive and negative charges cancel each other out and form an area around the junction with no moving charges, called the depletion area. The depletion area creates an energy barrier between the remaining positive holes and the free extra negative electrons. This prevents any further movement of charge across the junction. The energy barrier is represented by a kink in the energy band model, like this. So, in a diode, you have a positive region that is separated from a negative region by a neutral region. This explains why the learners found that there was a potential difference across the diode, even when there was no current passing through the circuit. Have you seen this before? Doesn't this remind you of a charged capacitor? When the battery was disconnected from a charged capacitor, there was still a potential difference across the plates. So, in some ways, a diode and a capacitor are similar. In both these components, there's a potential difference even when there's no current in the circuit. But a diode and a capacitor behave very differently when connected into a circuit with a battery. Have a look at what happens. In a diode, we can make the N-type side more negative by connecting it to the negative terminal of a battery, and the P-type side more positive by connecting it to the positive side of the battery. When we do this, we force lots of extra electrons and holes into the junction. The electrons in the N-type region near the junction are repelled by the electrons of the atoms of the P side of the junction. However, they're also repelled by the other electrons drifting around inside the N-type material. When we shove extra electrons into the N-type material, we increase the number of electrons pushing from this side. This works a bit like pressure in a gas. Electrons near the junction are helped across the junction by being shoved from behind. The effect is to reduce the amount of extra energy required to cross the junction. In other words, the height of the energy barrier, or kink, reduces, and electrons can move freely towards the positive terminal of the battery. In the same way, holes can move from the P-type material across the junction towards the negative terminal of the battery. When we connect the P-type end of a diode to the positive terminal of a battery and the N-type end to the negative terminal, like this, we say the diode is connected with a forward bias. Look at what the ammeter and voltmeter readings are when the diode is connected with a forward bias. But if we change the electrodes around, the ammeter reads 0 amperes and the voltmeter shows a negative reading. This arrangement is called a reverse bias. Let's see why no charges are moving across the PN junction now. The holes in the P region move away from the depletion region towards the negative terminal of the battery. In the N region of the diode, the extra electrons are pulled away towards the positive terminal of the battery. This increases the force of repulsion of the ions and stretches the depletion area, making it very difficult for charges to move over the junction. So charge cannot flow through the circuit. I hope you can see that for low potential differences, a diode is a very effective way of controlling the direction of current. Current can only pass across the PN junction when the diode is connected with a forward bias. But remember that if a very high potential difference is applied across an insulator, electrical breakdown can take place. This is also true for a reverse bias diode. A high potential difference will force charge across a PN junction, even if a diode is connected with a reverse bias. There are many different types of diodes, and one that is used very often is the LED, or light-emitting diode. These are useful because they emit light when current passes through them, and so are often used to indicate when a device is on or off. Let's take a closer look at how they work. In all diodes, when electrons from the N-type material cross over the junction to fill a hole in the P-type material, the electron moves from a high energy state to a lower, more stable energy state. This process is called recombination. During recombination, energy is released. In materials like silicon and germanium, this energy is released in the form of heat. But in some materials, like gallium, the energy released is the same as some visible light frequencies. This is called radiative recombination. When the surface of a diode made from a material where radiative recombination takes place is exposed, the diode will emit light. The color of the light depends on the band gap energy of the material used to make the diode. The term band gap refers to the energy difference between the top of the valence band and the bottom of the conduction band. For example, gallium arsenide phosphide produces a red or orange light because of its particular band gap. When the band gap is different, the color of the light emitted will be different too. Today, you can find LEDs being used as an alternative light source to the normal light bulb. They are used for emergency lights and torches and are being tested for use as traffic lights. Now, for today's task. Write a report in which you compare LEDs and light bulbs as a source of light. Your report should include what you think the advantages and disadvantages are of using each of these components. You should also make a prediction about the type of lighting that will be used in future homes. Now we have come to the end of this introduction to electronics, but remember that there's a lot more to learn. If you continue to study electronics, you will find out how transistors, inductors, and integrated circuits work. These components have made it possible to make radios, TVs, cell phones, robots, computers, and even satellites that have been sent to explore the boundaries of our solar system. But electronics are being used to cross other boundaries too. Each year, electronic components are getting smaller, and one of the newest areas of research is in the field of nanotechnology. It seems that in the not too distant future, electronics will combine with biotechnology, and tiny machines will be used to improve our health and even our memory. Who knows, the bionic man may not be a fantasy story for much longer.